in the cells and in the mitochondria. So at first what we did, the data that I'm showing you, it's now just for endothelial cells derived from iPS cells, because we are still having some issues with confocal microscopy, but as soon as we have the data for Huvector cells, then I will also share it. So as you can see here, again, we kept the 24 hours time point for us, and then we started to go for different concentrations of cyclosporin A. Here in the left part, we see a negative control, and we see that by increasing the cyclosporin A, I mean, even with low concentrations of cyclosporin A, we see a huge effect of ROS activation in our endothelial cells. Okay, this dye that we did for flow cytometry, which is the DCF staining, it's measuring all the ROS in endothelial cells. So we wanted to see if the ROS is in total increase in endothelial cells. How is ROS activation in mitochondria of endothelial cells? So for that, we use the DCF to measure the whole cell ROS, and this is the green dot in the confocal microscopy. And we use also H2X dye, which just measures the mitochondria's dye. And as we can see here, mitochondria's ROS, I'm sorry. As we can see here, in untreated cells, the control cells, the green dots are high. I mean, we have both red dots and we have the green dots. So we know that we have the ROS in among the cells, but in right we just see the red dots, but we do not really see the specific dye from mitochondria ROS, which means that it seems that mitochondrial transition pores are closed, so ROS cannot go out of mitochondria, and because of this, we cannot see the mitochondria specific ROS around the mitochondria and in the cytoplasmic of endothelial cells. And then we wanted to see if ROS is trapped in mitochondria, so if it's affecting angiogenesis or not. And as we can see here, we have different groups of cyclosporin A, and we have this control group, and we did the sprouting assay to check the angiogenesis of endothelial cells, as I very short described to you about this assay. And we have 2 cell lines about it, and our 2 cell lines. And as we can see, we measure the accumulative length of sprouts coming out from the spheroids. So as we can see, we have a control group, we have a VEGF treated group, and we have different concentrations of cyclosporin A. And as we can see here, after 5 micromolar of cyclosporin A, sorry, it was not COVID. So after 5 micromolar of cyclosporin A, we see a significant decrease in the sprouts coming out from the spheroid, which shows the angiogenesis impairment after cyclosporin A treatment on endothelial cells, which is again in parallel to our hypothesis that cyclosporin A is inhibiting angiogenesis of endothelial cells. So I also put here, as you can see here in bottom, 2 cytotoxicity curve or Rezazurin curve, just to show you that at this time point, at 5 micromolar concentration of cyclosporin A, the cells are still alive, so cells are not dead. And this decrease of angiogenesis is not because we are missing the cells, it's because of the phenotypic that the ROS, it seems to be trapped, so angiogenesis cannot go on normally. Or there are also other pathways for sure, because we know that this is not the only pathway happening in the cells, but this was one of the features that we could show. So then we did some temposec analysis for the ESR3 cells, because we didn't have the opportunity to do it also for Huvector cells, but I thought maybe it's good just to put it here. So we did some quality control because we had some low read counts in our temposec, so we excluded all the low read counts. And then here you see the PCI. These pink ones are the controls, and these are the treatments that we see that controls are clustered together, treatments are clustered together. And as we can see, so we had 3 concentrations. We had 0.31, 0.62, and 1.25, because we wanted to keep the concentrations close and similar to other studies like ROS and ATP and angiogenesis. And as we can see that we have differentially expressed genes in different time, and then we had different time points, 8 hours, 12 hours, and 24 hours. And the reason we didn't go for higher concentrations and higher time point is that because in TempoSec we are checking the RNA transcriptome of the cells. So we didn't want to go for example, for IC50 or something. We wanted to stay in sublethal concentration, 0 than IC even 10. So even having IC5, sorry, to know really what's happening in transcriptomic of endothelial cells. And so we did lots of analysis, but I don't want to talk a lot about it, so to not waste your time. But then we did the pathway analysis for all these concentrations, all these time points, and as we can see here, we came across 2 really nice pathways. So we could see the VEGF pathway, angiogenesis pathway, mitochondrial activation, mitochondrial dysfunction, ROS activation, toll-like receptor, and with this information, we thought, okay, we have this putative AOP, and this information also can help us to decide how to measure each key event in a more informative way. So I just also want to say about that we did some weight of analysis. So due to OECD guidelines, we did weight of analysis for Bradford Hill concentrations, and as you can see for each our key events and some key event relationships. And as you can see here, the essentiality for each key event is really high in literature reviews, which was really cool for us. And for the key event relationships, for some key event relationships, we have strong evidence based on biological plausibility and empirical support, and in some of them we have moderate or weak evidence that can help us to for further studies, for next studies, to see how we can go on with it to be able to develop a QAOP for this. So I hope you are still there. This was my first study. So I hope you're not bored and you're listening to me. You're not sleeping. I was not so slow. Everything was good. And the story was exciting for you. I know I was so fast, but let's go to the next study. I promise to talk very less about it. Because after having this data, so maybe it is correct. No, it's not. And as I'm working in Evercyte company, and they are doing a very nice job in the EV field, extracellular vesicle field. So we thought maybe it's good because now we see the effect of cyclosporine on endothelial cells. So maybe it's cool to see if these extracellular vesicles can do a bioactivity in chemical part. And I think it's one of the novel studies that shows the linkage between bioactivity of extracellular vesicles with chemically affected or chemical safety studies, something like this. So we use the Wharton jelly, mesenchymal stem cells, derived extracellular vesicles. So at first, and these EVs are produced in Evercyte with my colleagues, through my colleagues, and these are derived from mesenchymal stem cells, which are immortalized in Evercyte as well. So at first, I did the angiogenesis property of endothelial cells, and as I showed you, so I don't go through it a lot. So, but we can see that we have a control and we have a VEGF treated cells, that we have more accumulative length in VEGF treated cells, endothelial cells, which should be obvious. And then we did a characterization for this extracellular vesicle. We did some Western blot and we did some FACS analysis for that, to show that our EVs are EV. So I don't want to go in more details because I don't want to take your time. And then we wanted to see, because as you can see here is the control, and this is the accumulative length of control that we see some sprouts coming. When we treat the cells with VEGF, obviously, and as it should be, endothelial cells are starting the angiogenesis, so we see sprouts coming out from the spheroids. If we use cyclosporin A, as we see in our last study, it's inhibiting the angiogenesis, and here we can see it again. And then we started to study the EVs, extracellular vesicles. If we put only EVs on the cells, we see again an increase in the sprouting, which is, I think it's cool. And if we put the cyclosporin A plus EVs, again, we see this effect and we see this increase, which is showing that it seems EVs are inhibiting the anti-angiogenic effect of cyclosporin A. And here is just a control, a positive control group, which has the VEGF, cyclosporin A, and Vartongeli EVs. So it was really cool for us that we see that Vartongeli MSC TERT 273 EVs at concentrations of 10 to the power of 5 EVs per cell can increase angiogenesis in endothelial cells, and they can inhibit the effect of cyclosporin A. And then we wanted to see, since cyclosporin A is activating ROS, is EV at this concentration inhibiting the ROS activation? And as we could see here, it seems yes, because this is the negative control, which should not increase the ROS. This is the group treated with cyclosporin A. As you can see here, we see a clear shift to right part, which shows the ROS activation in the cells. And if we again treat them with this concentration of EV, we again see a left shift to, and it shows that if you look at the median, we see a less median, and it shows that it's decreasing the ROS activation on the endothelial cells. And this is another concentration, just to be sure about it. And this is also a negative control. So for this study, the next level would be to prove this effect by some antioxidants. So yeah, this was a brief description about my next study. And then I'm also working on a joint publication with my other colleagues about public and private mechanism of paroquat, that I'm sure that my colleagues will cover it very well, so I don't bother you a lot. So I just want to thank for all your attentions, my nice and best colleagues in in3 project, and Evercyte, Marie Curie, and LBI, and wish you a very nice day with us. Thank you.